All right, it's 5:30, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, hanging in there. We have we're basically winding down the semesters. We have 4 more lectures to go, and then we'll be done. Okay. So I know on the schedule I said this week we're doing ANSYS activity 8. I did want to take a day to talk about fluid mechanics simulations because I know this was a request from a few people. So today we're gonna go over fluids. Thursday we'll probably talk about ANSYS activity 8. So we're gonna have an introductory lecture about buckling. We may be able to get the activity done on Thursday as well. Remember, ANSYS activity 8 is not one that I'm collecting. It's mostly just there if you were interested in doing it for your projects. And so we may be able to get both the lecture and the activity done on Thursday. That way, next week we can have just open office hours or just cover whichever topic that you want me to cover in the class next week. Okay. All right, but today we are going over fluid mechanics simulations in ANSYS. So I made this handout about 5 years ago now. Wow. Back in 2020. And it's just going to go over just the basics of fluid mechanics simulation. So first part of today is just going to be a little bit of a review of fluid mechanics in general. And so if it's been a while since you've taken fluids, or if you've never taken fluids before, this first part will just kind of introduce you to some of the terminology, some of the concepts that's needed to run fluid mechanics simulations. And then we're going to end today with kind of an interactive activity that we're going to do together. Okay. All right. Any questions? So I know a couple of you have sent me emails about your project. I'm a little bit behind on my emails just because first couple of days this week have been a little bit busy for me. But I will get to your emails by tomorrow. So just kind of sit tight for now. I'll answer your emails. I'm a little behind just because registration for the undergrad has been a little bit hectic this end of this semester, but I'll get to them. Okay, all right, so let's go and get started. Okay, so I didn't print out these notes, and so I'm just going to kind of just show the handout. So this is a handout that's available to you online on Canvas. And so if you go to the Canvas site, you go under lecture notes. This is handout A5 right here. So this first part of the handout here is just a little bit of fluids review. So I'm just gonna show the figures and show the equations and talk over it. I'm hoping that the most of today's is going to be focused on the interactive part itself. Okay. Okay, so let's talk fluid mechanics simulations. And so the interesting thing about finite elements is that even though for the majority of this class we've been focusing just on structural FEA, and I would say that that's what most people associate finite elements with in practice is the structural side. Finite elements is actually a very general methodology that you can use to simulate any kind of physical phenomenon. So basically, if the physical phenomenon that you're trying to model is governed by a differential equation, you can simulate it within ANSYS, and fluids is no different. Okay, and so fluids, as you may know, follows the very famous and very complicated Navier-Stokes equations. Okay. So I've written out the Navier-Stokes equations for you here. So basically the Navier-Stokes equations represent conservation of mass and momentum in a fluid. So you don't have to write this down just because, we're not going to be solving it in this class, obviously. But this is just to illustrate to you that, fluids is no different from solid mechanics, is no different from heat transfer, where, we have a partial differential equation that we want to solve, and finite elements gives us a way to do that. Now, if you're talking about, so generally the term that's used to for computational simulations of fluid mechanics in practice, usually you've probably heard of the term CFD. So CFD stands for computational fluid dynamics. So finite elements for fluids does fall under the category of CFD. This is true CFD here, but if you're talking about CFD that a lot of other people use, that people use in industry, they typically use a different method called finite volumes. It's similar to finite elements. It's just the way that it's formulated and the way that the equations are made and the code is written is slightly different. So I would say finite elements for fluids is a little bit in the minority in terms of what people use in practice. Just because finite volumes it's a little bit more natural to simulate fluids with finite volumes, but you can still get great results with finite elements. Actually, all the work that I've done in the past with my research, I've always used finite elements for CFD. And so it's not that it's inferior, it's just that it's a little bit less common than finite. Okay. But if you're coming from a perspective of of a student in this class where we've done basically exclusively solid mechanics simulations, there's a little bit of a learning curve that comes with doing fluid mechanics simulations in ANSYS. Okay, probably the biggest adjustment that you have to make is the adjustment to the geometry that you need to use for the fluid mechanics simulation. Now, typically, for a solid mechanics simulation, you're probably accustomed to geometries that look like the following, where we have a CAD model of the solid parts of our geometry, right? And so if you want to simulate, I think the midterm project is actually a great example. So, a lot of you guys did the four-way valve for your midterm. And so that valve, we have a CAD model of the pipes themselves. In other words, the solid components of your geometry. And that's very common. And so, usually if you're creating a CAD model for design, for manufacture, you're going to make a CAD model for the solid components of your geometry, because that's the part that you're actually going to build, right? So that makes sense. But for fluids, this kind of geometry here actually will not work with the fluid mechanics simulation, okay? Because if you think about it, the fluid, fluid typically flows in these situations within the empty space in your model, right? So fluid is not going to go through the solid parts of your geometry here, right? The fluid is going to go in through the empty cavity in the middle, right? And so if you want to run a simulation of the fluid flow, you don't want a mesh of the solid components. You actually want a mesh of the interior of where the fluid is actually going to go, okay? And so, for these two models here, I tried to make it so that, they're taken from the same perspective with the same zoom in, right? This model, this cylinder model here is actually a CAD model of the interior of this pipe right here. So it's as if, you kind of filled this pipe with like Play-Doh or putty and you kind of pushed it out, right? This is actually the model and the mesh that we want to use for a fluid mechanics simulation, because this is where the fluid will actually go, okay? And so this is actually what we want for a fluid mechanics simulation. So I would say that's the biggest adjustment. And so, because typically when you make a CAD model, and most times when you obtain a CAD model from outside, it's going to be of the solid components of your model, right? But what you actually want for CFD is you actually want a model or a mesh of where the fluid is actually going to flow, okay? Which is something that looks like this. Now, there are tools, and because typically the vast majority of CAD models that you are going to inherit are going to be of the solid model of the pipes. So there are tools within the CAD softwares to get you this model here. And so I know a lot of you are using SolidWorks, and so there is a function within SolidWorks called invert geometry. Now, it's been a long time since I've used this, and so I don't know if they still call it this. But there is a way for SolidWorks to kind of smartly extract kind of the interior of your geometry for you to use in a fluid mechanics simulation. Okay, there are some limitations, and so if you have a fairly simple pipe geometry or a very simple valve geometry, this should work fairly well. But if you have a more complicated geometry where flow is going inside, outside, exterior, it may not work as well. So in those cases, you may want to construct your CAD model more manually in those. For fairly simple cases, there are some automated tools. Just be aware that there are some limitations. So in our activity today, I don't have a CAD file for you to download. Since we're just going to simulate flow in a pipe, we're basically just going to create a cylinder within design modular in ANSYS and then run the simulation. But that's kind of point number one, where if you are going to run a fluid mechanics simulation, you don't want a model of the solid part. You actually want a model where. Okay. Oh, actually, so another very common situation to run CFD is, let's say that you want to run CFD on some kind of exterior flow. Okay. So, the kind of the example that really comes to mind is, let's say that you have a car or some kind of vehicle, right? Wheels, and you want to simulate the airflow that's going over the vehicle. Okay, so just like this model that we have here, right? You want to have a mesh of the region where the fluid's going to go, right? Now, for an exterior flow, it's a bit more complicated because the flow is outside, right? And so your flow domain, actually in this case, is actually going to be a box, right? Where your fluid, which is air in this case, is going to flow all throughout the box, right? Except that now you're going to have a cutout, and so there's going to be basically a cavity within your box that's going to be in the shape of the object. And so let's say that you want to, simulate flow over car, you're going to have a hole in your box that's going to be in the shape of a car. And that's a car, not a dinosaur. Okay. So exterior flows it's doing exterior flow CFD is a little bit more challenging because you have to, create a box that's going to be big enough to hold your entire flow. And then you actually have to cut out a portion of that box, which is where your solid geometry is going to be. So I have gotten a couple questions on that. So I will say I'm a little bit less experienced with that, but that's typically how you would do it for, for an exterior, typically airflow type of simulation. All right, any questions on this so far? Okay. Okay, so let's talk some concepts. Okay, so I've already shown you this, and so the main equation that governs fluid flow here are the Navier-Stokes equations, and so this is the conservation of mass and momentum in a fluid. Okay. All right, so the main thing to know here is that because our equation is different, that means the variables that we're going to solve for are different as well. Okay. So the main thing to remember for fluids is that your primary variable is going to be the velocity. So when we did our solid mechanics simulations, our primary variable was the deformation. For fluid mechanics, our primary variable is the velocity instead. Okay, so that's going to be the first thing that these simulation solves for. Okay. Actually, and for fluids, we actually have a second primary variable, which is the pressure as well. So Navier-Stokes are actually going to solve for both the velocity and the pressure in the simulation. And that's actually kind of what makes fluids so challenging, is that you have to solve for both at the same time. All right. The other thing that's kind of unique about fluid mechanics simulation in ANSYS is that we actually use a separate program to run the fluids. And so there's another program within ANSYS called Fluid. So Fluid is, you want to know the history of this. Fluent actually used to be its own company, and then ANSYS kind of gobbled it up. It kind of just bought out the company and just duct taped it to ANSYS. And so, it's I will be the first to tell you it's not the cleanest addition. ANSYS kind of has a lot of tools that they kind of just duct tape onto their main interface, and so Fluent is that. So it's not consistent in terms of its presentation. The menus and stuff are all very different. So it's very clear that Fluid used to be a separate program. But that's how fluid mechanics simulations are done in we use a separate program. So, it's going to be a little bit messy. We're going to open up quite a few different programs within it, but this is kind of the best way. That's okay. All right, so first thing we're going to talk about is material properties. So just like our structural simulations, we need to specify material properties for our fluid simulations. Okay, and there are two main properties that we need to specify for our fluid. First is the density of the fluid. The other is viscosity. Okay. So density should be a fairly similar property here because that is a property of our solid materials as well. Okay, but instead of the Young's modulus and instead of the Poisson's ratio, which we've been using for our structural simulations, we are instead going to use the viscosity of the fluid. All right. So viscosity, I have kind of a whole lecture that I dedicate to viscosity for my undergrad, but basically the viscosity will tell you basically the stickiness of the fluid. So I think we've all kind of experienced certain fluids that just feel a lot more sticky than others. So if you think of like honey, honey is a very viscous fluid. Molasses is the other kind of very viscous fluid, and we've also experienced a lot of very thin fluids as well. So water, very thin fluid, so it flows very easily. Viscosity basically measures how sticky that fluid is, and it has a strong effect in terms of the fluid mechanics and the velocities and the pressures that develop in a fluid flow. Okay. So you need to specify the viscosity. That is a required property. See it. Okay. Now, the interesting thing about fluid properties is that they are very temperature dependent. And so actually, that's not too different from our solid materials, although fluids are much more sensitive to temperature than solids are. And so when you are specifying fluid properties, you need to specify the temperature at which you are specifying them, so that you can, get the right properties. Okay. So typically, when we assign fluid properties, we assign them at room temperature. So room temperature is approximately 5 degrees C. But if you have other situations where you have high temperature fluid, low temperature fluid, you want to make sure you specify the materials properties. Okay. Any questions on material properties, density, viscosity? The nice thing about fluid properties is that they're typically easier to look up. I think maybe I should say that the variety of fluids that are used in engineering practice is a lot smaller than the variety of different solid materials that you can use. And so for solid materials, we have all different kinds of metals, all different kinds of woods, composite materials, plastic materials. A lot of these materials are very proprietary in terms of how companies use them. So sometimes it can be very difficult, as you guys have probably experienced, to find Young's moduli, Poisson's ratio for certain materials, especially if you have an anisotropic materials. The nice thing about fluids is that most fluids are either going to be water or air, and even the fluids that aren't water, they have properties that are very similar to water. So and so you can use properties of water and probably get away with it in situations. Unless you're working with a very specialized fluid like oil, something like that, then that is a bit different. But a lot of fluids, are either air or water. That's most of the fluids that are going to be working. Okay, so let's talk boundary conditions. And so, just like our structural simulations, boundary conditions play a very important role. But because our governing equation here is very different, that changes the nature of the boundary conditions that we are going to. Now, just like in structural mechanics, we're going to specify our boundary conditions either constraint type and load type. Right now, when we're talking fluids, these definitions kind of have to be generalized a little bit. But remember, for constraint type boundary conditions, we define these as boundary conditions that directly specify the primary variable, which, for our case, is going to be velocity. Okay? So any type of boundary condition that directly specifies the velocity of our fluid at a particular interface or a particular surface, we're going to consider those as a constraint type boundary condition. Okay? Now, our load type boundary conditions are kind of like everything else. And so our force boundary conditions, our pressure boundary conditions, those are typically the boundary conditions that we're accustomed to in our solid mechanics simulations. For our fluid mechanics simulations, a typical load type boundary condition is going to be a pressure boundary condition. Now, I know I mentioned earlier that pressure is a primary variable, and that's true for the governing equations. But for the boundary conditions, typically a pressure type boundary condition, we classify that as a load type. Okay. and you'll kind of see why in a second. Okay. Okay, so let's talk about the constraint type boundary conditions first. And so, for constraint type boundary conditions, we have, we can just straight up specify the velocity. Or another common way to specify the constraint type boundary condition, mass flow rate. Okay? Where you specify the mass flow rate of a fluid that's coming into your model. So mass flow rate, typically we give it the symbol m dot. So mass flow rate typically has the units kilograms per second. And so it's literally the amount of mass that's passing through this interface per second, right? And so we can typically convert this to a velocity just by simply dividing it by the density and then dividing it by the cross-sectional area as well. M dot, we divide it by the density, rho. We divide it by the cross-sectional area, AC. This will give us the velocity. So even though mass flow rate is technically not a velocity boundary condition, we consider it a velocity boundary because there's a direct equation that lets us compute velocity straight from the mass. Okay. All right, so that's very typical, and so you're going to see in the example that we're going to do, we're going to specify a mass flow rate. Okay. I had the equation down here, and so this is the equation to convert a mass flow rate to a velocity. But also you can apply just a direct velocity and that's going to have what's called a flat velocity profile, where the velocity is just going to be constant and constant. Okay, so that's the first part that you're going to need to solve a CFD. Is you need to have an inlet boundary condition. And so typically whenever flow is entering your domain or entering your model, you're going to specify that as a constraint type boundary condition. Okay. Inlets, typically you're going to have some kind of constraint type boundary, either a velocity boundary condition or a mass flow rate type. All right, so I would say typically, if you have some kind of external flow, so you're simulating airflow over an object, I would say in those cases, typically you're going to specify a velocity type boundary condition. But for internal flow, so let's say flow in a pipe, typically we specify a mass flow rate type boundary. Now, those are just the typical ways that people do it. There are good reasons for it, but you can also swap it as well. So you could very easily have an internal flow where you specify a velocity boundary condition, or you can have an external flow with a mass flow. There's no rules against it. It's just that typically that's what's. Okay. Any questions on this so far? Okay. Good. Okay. Now let's talk pressure boundary conditions. And so for pressure boundary conditions, essentially what we're applying is we're applying a force per area on a surface. Okay, so in that sense, it's not that different from a structural simulation. Kind of draw an example here. Let's say we have a pipe. So if we apply a pressure here, that means that pressure is going to be applied across the entire surface as a force, basically distributed over the cross section. Now, this is very common in fluids to specify as an outlet boundary condition. So whenever you have fluid that's going to be leaving your domain, typically it's pretty typical to apply a pressure boundary condition in those areas. All right, so wherever you have regions where flow is exiting your domain, we typically call that an outlet. Okay. So whenever you have an outlet, typically you're going to have a pressure boundary condition in those. Okay, so that's what we're going to do. So intuitively or physically, the way that you can interpret this is that the pressure boundary condition, specifies what's called a back pressure. So a back pressure is something in fluid mechanics that's used to, resist fluid flow coming through. Okay, so to kind of summarize, for a typical kind of internal flow simulation, for your inlet, you're going to have some kind of constraint type boundary condition, so either velocity or mass flow rate. And then at your outlet, you're going to have some kind of pressure boundary condition to specify the back pressure. That's typically how it's done, especially when you're kind of first starting out in CFD. velocity inlet, pressure out. Okay. All right. So one thing you have to be careful of is that, it is possible. It is possible to have, pressure boundary conditions. So you have pressure at your inlet, pressure at your outlet. But one thing you cannot have, or unless you really, really know what you're doing, it's very difficult to have a velocity boundary condition. Okay. So this is very untypical here. So it's very untypical to change the outlet boundary condition to velocity. Why is that? Why is it uncommon to have two velocity boundary conditions? Let me give you an example. So let's say that, at the inlet here, let's say that we're specifying a mass flow rate. So let's say we're specifying a mass flow rate of 1 kilogram per second. We're specifying that amount of mass to be entering our model with 1 kilogram per second. Okay. And that's a very valid boundary condition that you could specify. At the outlet, let's say that we specify another mass flow rate boundary condition. So let's say that we specify it as 2 kilograms. Right. And so in this situation, we have more mass leaving the system than mass coming in. Right. And so there are a lot of rules and a lot of laws in physics, but the one that you definitely cannot violate at any given time is conservation of mass. So it is impossible, at least to our knowledge, to create mass from nothing. And so if you have a boundary condition like this, where you have less inflow than outflow, then you're basically violating conservation of mass. Okay. Now, this is a very egregious case, right? And so, if you know what you're doing, you're never going to do this. But if you have a complicated system, so let's say you have a system with, multiple outlets. Right? So let's say you have flow coming in here, and that flow is being distributed to all of these different outlets here. Right? And so in this case, we have 7 outlets. If you want to specify a mass flow rate for all of these, you can do that. It's just that, you have to be very, very careful in how to make sure that they add up to 0. Okay. And it actually goes beyond that as well, because if you have an unsteady simulation, so let's say that your mass flow rate is changing with time, right? There is a possibility for flow to be temporarily stored within the model itself. Okay. Whether you have any kind of recirculating flow or so there will be times where, that, even if you are very careful, you may unintentionally kind of violate conservation of mass, especially with complex situations like this. That's why, people always tell you, the first thing they tell you when you first learn CFD is that, your inlet boundary conditions can be velocity or mass flow rate, but your outlet boundary conditions have to be pressure. And that's mostly to make sure that conservation of mass is satisfied, and you're not creating mass or destroying mass within your system, which can cause a lot of things to break. All right, so for all intents and purposes, especially if this is your first CFD simulation, velocity inlet, pressure out. Okay. Question. All right, question: can you do pressure inlet and mass flow outlet? You can as well. That is an option. It's just that, for most engineering systems, it's more common to have a single inlet and multiple outlets. And so in those situations, you typically want to limit the amount of mass flow rate that you want to specify on a CFD simulation. So you usually want to have 1, maybe 2. And so if you have a multiple outlet system, say 5 or 6, you don't want to specify 5 or 6 different mass flow. But it is possible. And so if you have a simple situation, you can do a mass flow rate outlet pressure. That's perfect. All right. Any other questions on this so far? Okay. Okay. So that's inlet and outlet boundary conditions. So very, very important consideration for when you're running CFD. Okay. All right. What about the walls? So typically the walls count as a boundary as well, right? And so the wall is any area of your model that you do not want flow to penetrate through. Okay. So in this situation, we have flow that's going from the inlet to the outlet. We want our flow to go this way. We don't want our flow to go past the wall. Okay. So for walls, there's a very specific boundary condition that we typically apply on the walls, which is called the no slip boundary condition. Okay. And so a no slip boundary condition basically says that the velocity at the wall has to be equal to 0. So that's the easiest way to prevent fluid from kind of escaping from your model and penetrating through the wall. All right, so whenever you're running a CFD simulation, it's really important to identify the wall so you can apply that no slip boundary condition. And you're going to see in the example that we're going to do that a big part of when we're defining our geometry is to actually define that wall. Okay. So that was kind of a speed run through just the setup for CFD. So obviously, there's a lot more that we could talk about, a lot more concepts with fluid, but I think that's at least enough to kind of get you started. Now, before we start jumping into the example, I did want to speak briefly about the common outputs that you can get from a CFD simulation. Okay, so the first output that you can get is a velocity, right? So just like we can output the deformation from a structural simulation, velocity is something that you can output because it is the primary variable from our Navier-Stokes equation. The velocity will tell you, the direction of and the direction and magnitude of the velocity at all points in your model. Okay. The only thing I would say is to be careful is that when you are displaying the velocity, typically we use a color contour that looks like this. So this should be hopefully very similar to what we've experienced in ANSYS so far. So when we specify the deformation and the stress, typically we display it as a color contour. But just like the deformation, right? Remember, deformation is a vector. And so not only does it have magnitude, it has direction. Now, in structural simulations, we didn't worry about that all too much because in structures, we can actually get ANSYS to display the deformation by actually deforming the model itself, right? So let's say that, if you have a cantilever beam, you apply a force, right? When you show that result in ANSYS, it actually looks like the beam is bent. So not only do we get the numerical values for the deformation, we can visually see, which direction the deformation is actually, moving within the model itself. Okay, that's not the case in CFD because CFD, right, in fluid mechanics, the fluid is constantly moving, and so it's a lot more difficult to visualize the direction of the velocity itself. Okay, so this is typically what you're going to see. So typically, when you view the velocity, you're just going to view a color contour, where the colors here just tell you the magnitude of the velocity. If you want to see which direction the velocity is going, you're going to have to utilize different tools. So one of the tools that we're going to use is something called the path lines, which we'll go over in a bit. But just know that when you display the velocity, it is technically a vector. It's just a lot more difficult to show. Actually, a lot of times when you show the velocity, a lot of times that when you see the direction, usually you kind of infer it just based on the shape of the geometry. So, okay. So in this particular case, we know the fluid is going from one end to the other. Okay. And so, we can kind of infer that the velocity is probably going this way. Turbulent structures notwithstanding. So, but just be aware that the velocity plot is a little bit more difficult to kind of interpret than that, just because we can't really visualize the direction as easily. Okay, another output that we can look at is the pressure. So pressure is, basically the amount of pressure that's being exerted by the fluid. Okay. Anytime you have fluid flow, we're going to have some differences in pressure. And so what you should be looking for here is that whichever direction your fluid's going. So let's say in this case, the fluid is flowing this way, right? Fluid always goes from high pressure to low pressure. So one thing, I always tell people is that, you should check your pressure plots just to make sure that the pressure magnitudes here are consistent with your direction of flow. And so you can see from this model here, we don't have that much pressure drop just because this is a fairly simple geometry, but the pressure does drop. And so it goes from a high pressure on the left side to low pressure on the right. So that tells us that the flow is going from left to right in this case, because flow goes from high pressure. So when you display pressure in your CFD simulation, you should see a very clear gradient where pressure goes from high at the inlets to low at the outlet. This is where the flow comes in, and this is where the flow comes. So that's, that's kind of the first thing that I look for, in CFD simulations. So, does my pressure distribution or my pressure contours, do they make sense, relative to the direction of flow that I would. Okay, so that's the pressure. All right, another very interesting output that you can get here is called the wall shear stress. Now, whenever you have a fluid that's flowing past a surface, right, because the fluid has a finite viscosity, right, there's going to be a little bit of drag in terms of, where the fluid kind of drags you along with it. Okay. And so that's basically the wall shear stress. You can think of wall shear stress as kind of almost like a frictional force. And so whenever you have fluid flowing across the surface, there is going to be a little bit of friction. I say friction. It's not true friction, but it's fluid friction. So the wall shear stress kind of denotes kind of that dragging force that occurs when a fluid kind of flows past a surface. Okay, and so you can show that within ANSYS itself as well. So you can quantify that and display that within. And so sometimes this is very relevant. Wall shear stress has a lot of kind of research applications. Typically for the work that I do, I typically look at wall shear stress a lot. And so, depending on your application, this could be something that you're really. Okay, and so the last output that we have here is the path lines. And so the path lines, this is typically how you're going to view the direction or the path that fluid takes within your model itself. Okay. And so, for this example here, the path lines are kind of boring because they're just flowing in one direction. You can see that all the path lines go from left to right. But you can imagine, if you had a little bit more of an interesting geometrical shape, the path lines will show you the direction of the velocity. And sometimes it can be really interesting. And so, for instance, one application that I used to work on was aneurysms in blood. So, if you don't know what an aneurysm is, sometimes what can happen in your bloodstream is that, you could have these kind of sacs that form within your blood vessels themselves, right? So why these sacs form is actually still a topic of research, but it actually changed the fluid mechanics of your blood flow quite an interesting way, because the flow might be coming in, and all of a sudden you have a very rapid expansion of the cross-sectional area. And so the fluid is going to want to try to fill that space, but it may not do so efficiently. And so it may try to round this corner. You may have kind of a pocket of recirculating flow within that aneurysm itself. And so a pattern like that is something that you can view with the path lines. Okay. And it may indicate something like, maybe flow stagnation, or residence time of the fluid in that area. And so, path lines can be really interesting if you have a pipe. For flow in a pipe, it's just kind of boring because the flow just goes in. Okay. All right. So I think that's it for the intro stuff. Any questions on the outputs for CFD simulations? Okay. All right. So let's get into the example. So the example that we're going to do is just very simple flow in a pipe. So we have flow that's coming in at a mass flow rate of 15 kilograms per second. It's going to be flowing in a pipe with a diameter of centimeters, and we're going to be applying a back pressure of 100 kilopascals. Okay. The fluid that we're going to use is water. So water has a density of almost 1,000 kilograms per meter cube, and it has a viscosity, dynamic viscosity of 8.9 times 10 to the minus 4 pascals a second. Okay, all right, so let's go ahead and open up Workbench. All right, so I don't have a CAD model for you to inherit here, just because it's fairly simple geometry. Let's just go ahead and make it from scratch. Okay, so first thing we're going to do is we are going to specify a fluent analysis. So let's go ahead and click and drag fluent from the toolbox on the left, and let's drag it into the project schematic. Okay, so we have our typical kind of project schematic here. All right, so first thing I'm going to do is I'm going to create the geometry here. So I'm gonna right click on geometry here. And just to keep things simple, I'm going to specify it as a design model or geometry. And so we're going to open up design modeler and then create this geometry from. Right, so luckily for us, geometry is fairly simple. It's just a pipe, and so we're just going to draw a circle. We're going to give it a diameter of 20 centimeters, and then just extrude it for 1 meter. Okay. Good. Okay, so let's go ahead and draw our sketch in the XY plane. And so I've centered the view on XY here. Let's sketch. Let's draw a circle. Okay, so I'm going to center the circle on the origin here. And then let's dimension this. Oh, okay, this is ginormous. Okay, so we want to make our diameter here 20 centimeters. So 20 centimeters is 0.2 meters. And so hopefully you guys didn't jump as I did. Hopefully you guys changed the units here. So I'm going to change this to 0.2 meters. Okay. I'm going to make it very, very small. So I'm going to zoom in just so we can kind of see. Okay, so first thing is we made our sketch. It's just a circle with a diameter of 20 centimeters. Okay, so let's go back. Okay, we have our sketch here. So let's extrude this. And so to extrude within design model, we're going to click on extrude here. And so after you click on the extrude tool, we need to specify the geometry that we want to extrude. So let's click on sketch 1, which was the circle that we just made. So go ahead and hit apply. So for our extrude tool here, we are specifying our geometry to sketch 1. And we're going to extrude this geometry to a length of 1. And so luckily for us, 1 meter is the default for the extrude. Okay. So once we have specified all the extrude parameters, we have specified our sketch, we've set our extrude length. Let's go ahead and hit generate. And so after hitting generate, it's going to execute the extrude operation. And you can see here that we've made our cylinder extruded 1 meter in the Z direction. So all we did was we made a circle in the XY plane. We gave it a diameter of 20 centimeters, and we just extruded to. All right. Any questions on the geometry construction here? Okay. And remember, we are making a geometry of the region where the fluid is going to go. Okay. So I know this looks like a solid cylinder. Right, but this is the region where the fluid is going to go. So imagine that there's a pipe that's kind of around this outside. Okay, so the pipe on the outside defines the solid part, and then we're making a mesh of the fluid part. All right, question from the chat. So in space claim design modeler, is there an invert geometry? I think there might be in space claim. I haven't tried it myself, but I think there is an invert geometry function within. If not, I think there might be one in the new CAD program within ANSYS called Discovery. But yeah, I just haven't had a chance to try it myself. So, if you want to open up the geometry in Discovery or Space Claim, I think you're more likely to find an invert geometry tool in those rather than Design Model. Design Modeler wasn't really made for CFD. It was kind of the first CAD software within ANSYS. I think ANSYS made Design Model before they bought. And so if you're importing a CAD model and you need to invert it, I would try Space Claim or Discovery. All right, any other questions on this step here? Okay, all right, so once you're done with the geometry, go ahead and close it. Close Design Modeler. And so next thing that we're going to do is we're going to specify our mesh. So go ahead and double click on mesh here. We're going to be opening up our second program for the day, which is ANSYS Mechanical. Right, so ANSYS Mechanical is our usual friend, so that's where we run our analyses in the past. But for CFD, we're actually only going to use ANSYS Mechanical to create the mesh itself. We're gonna create the mesh, and we're also gonna create what's called name selections as well. Okay, all right, so you double click on mesh from ANSYS Mechanical or ANSYS Workbench, and you should open up Mechanical, and you should see our cylinder here. Okay, and so if you select the exterior surfaces of the model, you'll see that there are 3 surfaces that we can test. And so we have the lateral wall, we have both of the caps. Now, before we mesh, we actually need to create what's called name selections for each of these surfaces, just so that we can apply boundary conditions. Now, you could always do this, and so this is not something that's unique to fluids. And so even in structural FEA, you could create name selections. It's just that in structural FEA, there was just no reason for us to do so before this. But you know, if there are certain regions of your solid model that you want to save and kind of name it a certain name, you can do that using this feature. It's just that in Fluent, we need to use this in order to apply it. Okay, so in order to create a name selection, you're going to left click on Model A3. You're going to go Insert. Okay. And then you're going to click on the first option from the menu, which is a name selection. Okay. And so if you read the tooltip here, it's basically going to let us select a group of geometry within our model, and then give it a name so that we can refer to it. Okay. All right. So we've created our first name selection here. The first one that I'm going to create here is the wall. Okay. Remember, for the wall, we have to specify a very special boundary condition there. Okay, so let's go ahead and click, after you created your name selection, go ahead and click on the lateral wall. Go ahead and click apply here. Okay. All right, and then to name this, we are going to hit F2 on the keyboard. We're going to call this wall. Okay, so make sure you do that because you know we need to make sure we specify a no-slip boundary condition. Since Fluent is a separate program, it's going to be a lot more difficult for us to click on the different surfaces of the model. And so, you know, the idea is that, you know, while we have this mechanical interface up, you know, is to create these name selections just so that applying the boundary condition a lot easier once we get to that. Okay, let's go ahead and create another one. So let's left click on or right click on name selection, go ahead and create a new one. And let's create a name selection for one of the caps. Okay. Now this cylinder is symmetric, and so it doesn't really matter which cap you call which. But I'm going to call this cap the inlet. So I'm going to rename this. Okay. And so this is going to specify where flow is going to enter our cylinder. All right, and then I'm going to create one last name selection for the outlet. So right click on name selection, click on that, click on this. Okay. Click on the other cap that you didn't click. So, you know, don't click on the same cap that you did. And then we're going to call this out. Okay. All right, so you should have 3 name selections here. So you should have one for the wall, one for your inlet, and one for the outlet. Okay. It doesn't matter which of these caps is the inlet or outlet. The only thing that matters is that they're big. Okay. Any questions on this? Okay. All right. So next thing that we need to generate here is the mesh. And so, you know, for the mesh for this case, I'm not going to be too picky. The only thing I'm going to specify here is the size. For the size here, let me see what I use. All right. So in the handout, I used a mesh size of 15 millimeters. Go ahead and go with it. Okay. So I'm just gonna click on mesh here and then change the element size to 15. Okay. You can create a meshing object if you want as well, but I'm just All right, so let's go ahead and generate our mesh. So it should mesh very quickly. This is a pretty simple geometry here. And so you should have a good mesh. And since we were pretty small with our mesh size, you can see that we actually were able to make a hexahedral, you know, with this mesh size. If we check the number of elements, we have about 26,000 elements, which, you know, for a solid simulation or structural simulation, that is a little bit on the higher side compared to what we've done. But for a fluid simulation, this is actually very, very light. One thing about fluid simulations is that you typically need more elements for your fluid simulation than your solid one. And so, don't be afraid to push the element. One thing that's interesting about Fluent and ANSYS is that the count for the student version is actually higher. So I don't know exactly what the element count is. But I know for structural simulations, the limit to about maybe 64,000 elements. I know for fluids, I think you can push it up to 128. It may be even more than that. It may go up to 256, but you can push the element count a bit higher for your fluids. Just because a lot of times you need it. Because a lot of times for fluids, you need a very strong mesh density in order to get. Okay, any questions on this so far? Okay, question in the chat, let's see. Question, so do we need to do a mesh convergence test for this? So technically, yes, and so if you are going to be running a fluid simulation for your final project, technically it's going to be a separate mesh, and so I would like to see a separate mesh convergence test for the fluids. Good question. Okay, all right, so once we're done with the mesh here, we're actually all done with mechanical, so let's go ahead and close out of mechanical. Okay. I know we're running so many different programs today. Okay. Now, one thing you're going to notice, before we jump into Fluent, is that our mesh actually has a lightning bolt. And so what that means is that, ANSYS recognizes that we created our mesh, but we haven't finalized it yet. And so, what ANSYS actually needs to do is it needs to take your mesh and then merge it together with the named selections that we created. So basically, it's going to specify which nodes and which elements are going to correspond to which name selection that we create. And so to kind of make that matching and to tell ANSYS that our mesh is kind of finalized, at least for this run, we need to update the project. And so from ANSYS, you should see here that there's a button called Update Project. So go ahead and click that. Okay. Okay. So when you do that, it's going to be mating together the mesh with your name selection. It doesn't take this long. And so what should happen after this is done is that your mesh, the symbol next to your mesh should change from a lightning bolt to a green check mark. So there we go. Okay. So once the mesh has changed to a green check mark, ooh, it's actually doing it may be actually running the simulation. That's why it's doing this. But we're going to actually go in and change the boundary conditions. A faster way to do it, and so typically, actually, what I typically do is that you can right click on mesh, and there should be a button there that says update the mesh. That might be slightly faster than clicking update. Being the person that I saw a new shiny button, I wanted to click it. It looks like it's not doing anything bad. It's just just taking a bit longer. Okay. All right, so this is kind of what I expected here. So it tried to run the simulation, but it couldn't because we didn't have any boundary conditions. So we're actually going to go in and change that. So if you want to make this step a bit faster, if you just right click on mesh, you can just click update here, and then it's not going to update the entire front. Okay. So once you have that green check mark next to mesh, let's go ahead and double click on setup here. And so that's going to open up ANSYS Fluent. Okay. All right. So when you double click on setup, it's going to ask you some settings here. Okay. Now there's a lot of settings that you can specify here. And so if you want to run your simulation in parallel, you can do that. You can specify where you want to or where the Fluent executable is here. There's a lot of other things that you can do here, but for us, we're just going to use the basic option. So just go ahead and click start after this window comes in. Open up our third program of the day. So we opened up design modeler, we opened up mechanical. Now we're opening up Fluent. Okay. Maybe an ad that pops up. Want to change the theme. All my friends think I'm a terrorist because I like to use light themed on my stuff. They think that, my eyes are just, my eyes are just completely cooked. And so if you like dark theme, you can pick dark theme, but I'm gonna stick to my personality and go with them. Okay, all right. So after you've opened up Fluent, you should see your cylinder here, right? Or, and we're going to move into final production. So last things we need to specify here, now that we have our mesh, is we need to specify the material properties of the fluid, we need to specify our boundary conditions, and then we're going to run our simulation. Okay. Okay, so first thing we're going to do is we're going to specify the turbulence model. Now, this was something I didn't mention before, but whenever you're running computational fluid dynamics, oftentimes you're going to run into what's called turbulent flow. Now, turbulence is a can of worms that I don't want to open up right now because it's not something we can cover in 20 minutes of class time. Honestly, we can have an entire semester talking about turbulence. But it is an important part of CFD. And so when you open up this tab here called models, right? You'll see that there's a lot of different options that you can specify for the for the turbulence. Okay. Okay, so to change the turbulence model, you can do so by double clicking on this viscous SSDK omega. Okay, and you'll see here that there are lots of different turbulence models here. Okay, so all these different turbulence models, these are different ways to simulate turbulence in a CFD simulation. So if you're familiar with fluids, you probably recognize some of these. But for now, for our simulation, we are going to ignore turbulence entirely. And so we are going to run a completely laminar simulation. Okay. So that's the first thing we're going to do is that, first thing we're going to change the viscous model here. So double click on viscous and change the model here to laminar so that we're not having to deal with any kind of. And when you're first starting out with CFD, I would definitely recommend choosing laminar, just because turbulence is a whole can of worms. Okay, so that's the only thing we're going to do in the model portion. Okay, next thing we're going to specify here are the material properties. So go ahead and click on this arrow for the for material. Okay. And then we're going to expand the menu here for fluid. Okay, so right now we have one default fluid that's added, which is air. But let's go ahead and add our material properties for water. So let's right click on fluid. Let's click on new. Okay. All right, so let's go ahead and create a new material here. So let's call this water. And you can see here that there are two materials that we have to specify, two properties that we have to specify here. So we have to specify the density as well as the viscosity. Okay. Okay, so the density of water that we mentioned before, density is 999 kilograms per meter cubed. Right. And then our viscosity that we're going to specify here is 9.4, or excuse me, 8.9. 8.9. E minus 4. Okay, so that is the properties of water. So go ahead and click change create. Okay, and so it's going to ask you if you want to overwrite air. You could overwrite air if you want, but we're not going to use it. Or if you say no, it's going to create a new property here. That's the properties of water. Okay, good. All right, and so to actually apply this material property, we're going to click on cell zone conditions here. Okay. Right, and so the way Fluent works is that you can specify different fluid properties for different parts of your model. Let's say you have different portions with different fluids. Okay. Okay, so to specify fluid, to specify water here, we're going to double click on solid fluid here. And then we're going to specify the material that we're going to use here. So the second menu that comes up, there is a portion here called material name. We're going to change that to water. And just go ahead and hit apply. Okay. And hit apply twice if you're CT. Okay, so that should apply water as the material property. Okay. Okay, good. All right, any questions so far? So far, all we've done is just specify material properties within fluid itself. Okay, good. Okay, so next thing we're going to specify here are the boundary conditions. So let's go ahead and click on the plus arrow here. Okay. And you can see here that we have conditions for our inlet, we have conditions for our outlet, as well as our wall. And you can see here that, you know, all three of our name selections here have been sorted into these different categories. Okay. Let's check the wall properties first. So let's double click on wall. Okay. And so that's going to allow us to specify the properties for the wall. And you can see here that the condition for the wall here is no slip. Okay. So that's good. So that's what we want. So we don't have to change anything here. Because remember, we want our wall to have no penetration of fluid through it. Okay, next thing we're going to specify here are the inlet conditions. So let's double click on inlet here. And remember, we want an inlet boundary condition of 15 kilograms per second. Okay. Okay. So for the inlet here, you know, we have different ways that we can specify the inlet boundary condition. Okay, so the way that we're going to do this is let's go ahead and specify it in terms of components, just like we usually do. Okay. All right, let's see. It's slightly different than actually, let's do this. So let's right click. Okay. Yeah, so I apologize. So first thing we need to do is we do need to specify the type of inflow that we want. Okay. So if you right click on inlet, you can go down here to type. Let's go ahead and change it to a mass flow inlet. Okay. Okay, so that way we can specify the mass flow rate of our our inlet boundary condition. Okay. Okay. Okay, so mass flow rate here, we're going to specify it as kilograms per second. So let's go ahead and specify that as 15 kilograms per second. Okay. All right, and then we're going to specify that normal to the boundary. So let's go ahead and hit apply. Okay, so that should specify a mass flow rate of 15 kilograms per second going into the model itself. Okay, and then for the outlet, looks like our outlet boundary condition is already specified as a pressure outlet. Let's go ahead and double click this. Okay. All right, and then let's go ahead and specify the pressure for our outlet. And so our pressure for our outlet in this case is going to be 1 times 10 to the 5th. Let's go ahead and specify this as 1 E5 so that we have some back pressure back there. And then all the other all the other settings here, we can just keep the same. So for our outlet pressure, just make sure to specify that as 1 times 10. Any questions on the boundary conditions so far? I apologize, I'm going a bit fast just because we're almost out of time. I want to make sure we get to the simulation results. Okay, good. Okay, so now that we've specified the boundary conditions, we've specified our material properties, we're just about ready to run our simulation. Okay. Okay. So first thing we're going to do is we're going to go under solution here, right? And we need to double click this setting called initialization. Okay. Now, the interesting thing about CFD is that, it's very sensitive to your initial condition. So you want to make sure that you initialize your solution from a very kind of stable position. Okay. And so when you double click on initialization, we're just going to use the standard initialization here. Okay. Or the hybrid. And just go ahead and click initialize. Okay, and so that is going to initialize our simulation. So that's going to, make that we're starting from a good point. Okay. And the last thing that we're going to do here is going to run our calculation. Okay. So you're going to double click on run calculation from the solution here. One thing you need to specify is you need to specify the number of iterations. And so, number of iterations, that basically tells you how many times you're going to iterate to get a solution. Okay. Basically, the more times you iterate, the more accurate your solution is going to be. So for this simple case, I'm only going to use an iteration count of 10. But if you are going to use a more complex case, you may consider, adding additional iterations to your simulation. Right? Okay. So with our iteration count at 10, let's go ahead and click compute. Okay. Or calculate. And so this is going to run our simulation. Should be fairly quick because we have a fairly simple case. So your simulation should finish within a second or two. Okay. And so you should get a notification that says that your simulation is complete. All right, everyone that's following, everyone able to get a simulation done or the simulation complete? Okay, so we haven't looked at the results yet, and so that's the next thing that we're going to do. But everyone should at least get the box that says simulation complete for those that are following. Okay, good. Okay, so let's look at some results. And so to look at the results, you're going to go under results here, and you're going to click on this plus arrow next to graphics. Okay, so this is basically the main way that we're going to visualize our results, right? So the main place that you're going to visualize your results is going to be under contours. Okay, so contours basically displays your results as a color contour plot, basically the same way that we've always viewed our results within ANSYS. So let's go ahead and click new. Okay. Okay, so first thing I want to show here is the pressure throughout your simulation. Okay. Now, what's interesting about Fluent is that you can actually view your results. You can actually select which surfaces that you want to view your results on. And so I'm just going to go ahead and select all three of them, and we're going to view the pressure. So let's go ahead and click Save Display. And you close out the window, you should see the pressure distribution of your pipe. All right, so what you should see is that there should be a very clear pressure gradient within your model itself. Okay, and so you should have flow going from your inlet to the outlet. So you should have high pressure at the inlet, and then low pressure at the outlet. Okay, so for such a simple case, you should have a very clear pressure distribution just like that. Okay, let's see what else we can do with the contour. So let's go ahead and make a new contour. Okay, and instead of pressure, let's view the wall shear stress. Okay, so to view the wall shear stress, you're going to click on wall fluxes, and you're going to view on wall shear stress. Okay. Now, the wall shear stress, typically you only want to view that on the wall. So typically you don't want to view that on your inlet now. Let me go ahead and click display for the wall here. And we can view our wall shear stress. Okay. So you can see that a lot of our wall shear stress is kind of concentrated on one region of the model. Okay. But you can see here we have pretty consistent values all throughout. Okay, let's view the velocity. So let me go ahead and view our velocities. So let's view our contour with that. Let's go ahead and hit display. You can see our velocities here. And so, one interesting thing about the velocity is that, remember, for our boundary conditions, we specified the wall as a no-slip boundary condition. So there should be zero velocity on the wall, but at your inlet and outlet, you should have fairly significant velocities there. All right, and so if you have a non-zero velocity on your wall, then what I always say is that your model is bleeding, and so there's fluid kind of leaking out of the wall. All right, so last thing that we're going to do here is we're going to show the path lines, and to view the path lines, you're going to right-click on path lines here, click New. Okay. Okay, and so the only thing you need to specify for the path lines here is you need to specify which surface that you want to start the path lines from. Okay, so typically you want to start these from the inlet. So go ahead and click on inlet here, click Save Display. Okay, and so you should see the path lines from there. And so these path lines basically show you the path that the fluid is traveling along, as it goes through the pipe. And so it's going to come from the inlet and just take a straight path to the outlet. So again, the path line's not too exciting in this case, just because we have just simple flow in a pipe. But if you had some curvature, or you had some kind of branching paths, the path lines, would show something a bit more interesting. All right, any questions on any of that? Okay, all right, and so that is the very quick introduction to CFD. So if you wanted to use CFD for your final project, you know, this should at least help you get started. But what I anticipate probably happening is that, you know, for more complex geometries, the setup is going to be a bit more complex. So if you do want to run CFD for your final project, you know, I would say, you know, at least give it a try. But then when you run into issues, you know, definitely send me an email, let me know. You know, I could probably, it's probably a bit more efficient for me to work more individually with you, rather than kind of spend more time on it for the class. Because in the class, you know, there's a few more topics that I do want to cover, but I did want to do at least one day where we did CFD. Okay. But yeah, hopefully you guys enjoyed that introduction to CFD. There is 5 more minutes, and so if there are questions on your project that very quick that you want me to answer, I'll stick around for 5 minutes. If not, thank you guys for coming today. Thursday, we're going to start. We're going to introduce the concept of buckling. We may do the activity on Thursday as well, and so you know I'm going to probably try to get both of those done together. Remember, ANSYS activity 8 is I'm not going to collect it. That's mostly just for your benefit. So it'll be kind of similar to what we did today, except with a different topic called buckling. Okay. And so if I can save all of next week to just be open office hours, or you know, to cover just any topic that you guys want, I do want to save next week. Okay. All right. But other than that, thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Thursday.
Oh, so, did you go to another class? Yeah. Thanks so much.